The endless search for Earth 2.0. Imagine this. You are standing on the surface of a planet that is not entirely dissimilar to Earth. The sky glows a soft orange as a distant star sets behind the horizon. The air is breathable, the gravity feels just right, and the scent of foreign flowers fills the air. This is not Earth, but a place light years away, a distant twin that we have always been looking for. The question that fires our scientific imagination: could we ever find a second Earth? Ever since mankind first looked at the stars, we have been fascinated and tormented by the idea that Earth might not be the only habitable planet. Could there be other worlds where life as we know it thrives under the warmth of a sun-like star? In the late 90s of the 20th century, this question took on a new urgency. In 1995, astronomers discovered the first exoplanet orbiting a sun-like star, known as 51 Pegasi b, heralding a new era in space exploration. But 51 Pegasi b was a gas giant, far removed from a habitable planet. However, our dream has always been to find something more similar to Earth, a planet that could support life, with liquid water, a stable atmosphere, and the right distance from its star to allow biology to emerge. This dream drives the science of exoplanet research and guides telescopes such as Kepler and TESS in their mission to search the cosmos for worlds that resemble our home. Thousands of exoplanets have been discovered in recent decades. Some of them lie in the so-called habitable zone, that golden area around a star where the conditions could be just right for liquid water to exist on the surface. But what makes a planet habitable? And how close are we to finding a twin of Earth? As we venture into the infinite reaches of space, we encounter a bewildering variety of planet types that raise new questions about what it means to be Earth-like. From super-Earths to water worlds, each discovery brings us closer to understanding our place in the cosmos and where we might go next. Join us on this cosmic journey to discover these distant planets and imagine what life could be like on another Earth. What makes a planet Earth-like? To understand the search for a new Earth, we must first define what makes a planet Earth-like. It's not just about having land and oceans, it's about a delicate balance of conditions that make life as we know it possible. The Earth is located in a Goldilocks zone, not too hot, not too cold, in which liquid water can exist. After all, water is the universal solvent. Without it, life as we understand it cannot flourish. But the factors that make the Earth so special go far beyond the presence of water. Let's start with the basics, the distance to the star. A planet that is too close to its star would experience scorching temperatures, the water would evaporate, and a desolate desert world would be left behind. If you move too far away, the planet would become an icy wasteland. That's why astronomers are so focused on the habitable zone, or Goldilocks zone, a region around a star where conditions could allow liquid water to collect on the surface. But it's about more than just distance. Take Venus, for example. It is in the habitable zone of our Sun, but its dense atmosphere traps heat in a runaway greenhouse effect, making its surface hot enough to melt lead. At the same time, Mars, at the outer edge of the habitable zone, may have had water billions of years ago, but today it is a dry, frozen desert with only traces of its former water sources. So what else does a planet need to be Earth-like? A stable atmosphere is crucial. The Earth's atmosphere is a delicate cocktail of nitrogen, oxygen, and trace gases such as carbon dioxide, which regulate the planet's temperature through the greenhouse effect. This thin shell of gases also protects us from harmful solar radiation and meteorite impacts. Without an atmosphere, as on the Moon, the temperatures on the surface fluctuate extremely between extreme heat and cold. Another decisive factor is gravity. If a planet is too small, like Mars, it does not have enough gravitational pull to hold a dense atmosphere, and its surface could be exposed to intense cosmic rays. On the other hand, if a planet is too massive, like the gas giants Jupiter or Saturn, its gravity could crush potential life forms or accumulate a thick, unbreathable atmosphere of hydrogen and helium. Then there are magnetic fields. The Earth's magnetic field, which is generated by the movement of molten iron in its core, acts as a protective shield against harmful cosmic and solar radiation. Planets without a magnetic field, such as Mars, are exposed to the solar wind, which can strip away their atmosphere over time. Finally, we must not forget plate tectonics. This may sound like a purely geological process, but it plays a crucial role in maintaining the Earth's climate. The slow movement of the Earth's plates recycles carbon dioxide between the atmosphere and the crust and regulates temperatures through the greenhouse effect. Without plate tectonics, carbon dioxide could either accumulate in the atmosphere, leading to Venus-like conditions, or be trapped in rocks, resulting in a frozen, lifeless planet. With these key factors in mind, scientists are constantly refining their search for Earth-like planets. But could other planets that do not exactly match the characteristics of Earth also support life? What if we find life on a planet with a dense atmosphere, vast oceans, or a different chemical composition? Could life forms thrive there that exist under completely different conditions? This leads us to a deeper question. Are we limiting our search by looking only for Earth twins? Or could life also thrive in unexpected forms under conditions we can barely imagine? Super Earths, bigger and perhaps better? As our search for Earth-like planets continues, one particular class of planets has particularly captured the imagination of scientists, the so-called super Earths. These planets, which are around 1 to 10 times the size of Earth, offer a tantalizing glimpse of worlds that might even be more life-friendly than our own. Super-Earths are fascinating because they blur the boundary between Earth-like worlds and gas giants like Neptune. Many of these planets appear to have rocky surfaces and dense atmospheres, possibly characterized by exotic chemistry. But what really excites scientists is the idea that super-Earths could offer even better conditions than Earth in several crucial areas. Their greater mass means, for example, that they can hold a thicker atmosphere for longer periods of time, which would make them more resistant to solar and cosmic rays. An example of this is Kepler-4, 52b, often referred to as Earth's cousin, a super-Earth located about 1,400 light-years away in the constellation Swan. Kepler 452b orbits the habitable zone of a star similar to our Sun, and although it is about 60% larger in diameter than Earth, its potential to support life has captivated researchers. This larger size could mean that it has a stronger gravitational pull, which could help maintain a stable atmosphere for billions of years. Imagine standing on the surface of a super-Earth like Kepler 452b. Gravity would feel a little stronger, making everything seem a little heavier. Walking might be a little more difficult, but you'll soon get used to it. The sky above you might have a thicker, denser atmosphere that filters the sunlight in a way that makes everything look slightly different. Maybe the colors are more intense, the sunsets longer. If this planet had oceans, they could be huge and deep, perhaps with complex marine ecosystems. But there is more to super-Earths than just their size. Since they are larger, they could also have active tectonics and volcanism, similar to Earth. This geological activity could be crucial for maintaining a long-term atmosphere and regulating the planet's temperature. In fact, a more massive planet could remain geologically active for longer, which could provide heat and energy to support life below the surface, much like the volcanic vents at the bottom of Earth's oceans, where extremophile organisms thrive. Another fascinating aspect of super-Earths is their potential for different climate systems. With stronger gravity and denser atmospheres, the weather conditions on these planets could be significantly different from those on Earth. Storms could be bigger and last longer, but they could also help to distribute heat more evenly across the planet and prevent extreme temperature fluctuations. Another exciting possibility is that super-Earths could have huge oceans. GJ1214b, a super-Earth discovered 2009 orbiting a red dwarf star about 40 light-years away, could be a water world, a planet completely covered by a deep global ocean. With no visible land, life on such a planet could thrive in the deep, dark waters and feed on geothermal energy from the planet's core, rather than depending on sunlight. But despite all this potential, a mystery remains. Even though we have found many super-Earths, we do not yet know exactly what their surfaces are like, or whether they really offer the conditions required for life. One of the big questions is whether these planets have atmospheres rich in oxygen or carbon dioxide, which could indicate the presence of life or life-friendly conditions. Future missions, such as the James Webb Space Telescope, aim to study the atmospheres of these distant worlds in more detail. Could super-Earths be home to ecosystems that are even more complex than Earth's? And if so, would the life forms on such planets be similar to life here? Or would we discover something completely new and unexpected? As we explore these larger planets, one thing becomes clear: the universe is full of surprises, and super-Earths could be one of the most promising candidates in our search for new home water worlds, oceans without end. Imagine a planet whose entire surface is covered by a vast, endless ocean. No continents, no mountains, just deep, mysterious waters stretching for thousands of kilometers in every direction. These planets, known as water worlds, offer another fascinating possibility in our search for habitable planets. Although they may seem alien to us, they could be teeming with life in a way we never imagined. One of the best-known water worlds discovered so far is GJ1214b, which we have already mentioned. GJ1214b, a planet orbiting a red dwarf star about 40 light-years away, is larger than Earth, but could be completely covered by a deep ocean. The idea of an ocean planet is so captivating because water is a crucial component for life. Earth's oceans are home to a staggering variety of life, from tiny plankton to the largest whales, and we've only just scratched the surface of what might exist in the depths. So what could be lurking in the oceans of a water world? The first thing that comes to mind when you think of these water worlds is the depth of their oceans. On Earth, the average depth of the ocean is about 4.5 kilometers, but on a water world, the oceans could be tens or even hundreds of kilometers deep. The pressure at these depths would be unimaginable, far beyond what we experience on Earth. But this does not necessarily mean that life cannot thrive there. In fact, life exists on Earth in some of the most extreme environments, such as deep-sea hydrothermal vents, where organisms live on chemicals released from the Earth's crust without ever seeing sunlight. Similarly, life on a water world might be evolved to survive in the deep, dark oceans, possibly dependent on geothermal energy from the planet's core. If the planet is geologically active, underwater volcanoes could provide heat and energy and create a refuge for life in the deepest parts of the ocean. Imagine strange, bioluminescent creatures that have adapted to the enormous pressure and dark waters, floating through the depths and communicating with flashes of light, similar to the deep-sea creatures we find on Earth. Another important factor is the planet's atmosphere. In many cases, water worlds could have dense atmospheres that trap heat and keep the surface of the oceans relatively warm, even if the planet is far away from its star. This dense atmosphere could protect the ocean from the cold emptiness of space and maintain a stable climate. However, depending on the composition of the atmosphere, the planet could be constantly under cloudy skies or in endless storms. Imagine gigantic storms, bigger than anything we've ever seen on Earth, sweeping across the surface of the ocean with winds and waves that far exceed the strongest earthquakes. One of the most fascinating aspects of water worlds is the potential for underground oceans. Some water worlds could have a layer of ice on their oceans, similar to the moons Europa and Enceladus in our solar system. Under this ice, the oceans could still be warm enough to support life, protected from cosmic rays and the harsh conditions of space. This opens up the exciting possibility that life could exist on planets or moons that appear inhospitable on the surface but hide thriving ecosystems beneath the surface. Water worlds also force us to rethink our ideas of what a habitable planet looks like. On Earth, we are used to land and sea existing side by side, with life spread across continents and oceans. But what if life on a water world was exclusively aquatic? Could intelligent life emerge in the oceans and build underwater civilizations or develop technologies adapted to a watery environment? Although this idea is difficult to grasp, it is not completely out of the question. Finally, water worlds show us the diversity of planetary systems. These planets probably formed further away from their stars, where icy bodies accumulated and then migrated inwards, bringing their water with them. As they settled into their orbits, the ice melted and created vast oceans. In some cases, however, these planets may have migrated too close to their stars, vaporizing their oceans and leaving behind a waterless, barren world. But for those planets that remain in the right position, with a stable climate and deep oceans, the possibilities for life are immeasurable. Could a water world be our next home? That is difficult to say. While these planets may have the water necessary for life, living exclusively on or under the ocean poses significant challenges for human colonization. But they are an important step in our understanding of the variety of habitable planets that could exist in the universe. Rogue planets. Lost worlds in the void. Not every planet is lucky enough to orbit a star. Some drift through the cold, dark expanse of space without being bound to a solar system. These so-called rogue planets, also known as nomad planets, are among the most mysterious and fascinating phenomena in the universe. Although they lack the warmth and light of a nearby star, they could still be hiding secrets, and perhaps even the potential for life deep within their frozen, isolated surfaces. But how do planets become rogues? Rogue planets are probably formed by gravitational interactions, either with other planets or with passing stars that eject them from their star systems. In the early chaotic days of a solar system's formation, planets can fight for position, sometimes leading to violent ejection. These planets, torn from their home star systems, wander through the galaxy and drift into darkness. Without a star to provide light or heat, one might assume that rogue planets are empty, frozen wastelands. And many of them probably are. But some scientists speculate that internal heat generated by radioactive decay or even geothermal activity could keep a rogue planet warm enough to preserve liquid water beneath its surface. Imagine a planet with a thick layer of ice, similar to Jupiter's moon Europa or Saturn's Enceladus, with vast oceans hidden beneath the surface, heated not by a star, but by the planet's internal energy. This leads us to a fascinating thought experiment. Could there be life on a planet without a sun? On Earth, most life depends on sunlight, either directly through photosynthesis or indirectly via the food chain. But in the deepest parts of the Earth's oceans, where sunlight never reaches, life thrives around hydrothermal vents that use chemical reactions as a source of energy instead. If life can exist in these extreme conditions on Earth, it is not unreasonable to believe that similar ecosystems could develop on a rogue planet with underground oceans. Imagine explorers from Earth landing on a rogue planet and drilling through miles of ice to reach the hidden oceans below. What they might find there is left to the imagination. Could they discover simple microorganisms or even more complex life forms that have adapted to the dark, cold water? Would these life forms be completely different from anything we know? Or would they share biological characteristics with Earth's deep-sea organisms? These are the tantalizing possibilities offered by rogue planets. But not all rogue planets would be frozen. Some could be gas giants, like a drifting version of Jupiter or Saturn, without a solid surface but with huge atmospheres of hydrogen and helium. Others could be super-Earths with dense atmospheres that may store enough heat to keep their surfaces temperate, despite the lack of starlight. The presence of exotic ices and chemicals on these planets could also lead to environments far more alien than anything we find in our solar system. The idea of rogue planets challenges many of our assumptions about what makes a planet habitable. Without a star, conventional methods of planet detection, such as the transit method, become useless as there is no light for the planet to block. Instead, astronomers rely on the gravitational microlensing technique to detect these wandering worlds. When a rogue planet passes in front of a distant star, its gravity bends the star's light and amplifies it, creating a brief but detectable flash. This technique has already uncovered several potential rogue planets, although much remains to be discovered. What is even more astonishing is the possibility that there could be more rogue planets than stars in the Milky Way. Some estimates suggest that for every star in the galaxy, there could be 2 or 3 rogue planets drifting through space, invisible and unrecognizable unless they pass in front of a distant light source. If this is true, it means that the galaxy is full of planets we have not yet discovered, worlds that may hold the key to understanding planet formation, evolution, and even life itself. The prospect of rogue planets also raises important questions about the future of space exploration. Could these planets serve as stepping stones on humanity's journey to the stars? Without a star to provide energy, any human settlement on a rogue planet would have to rely on geothermal energy or advanced technology to survive. But these planets, if they contain water or other resources, could one day become important outposts in the vast, empty expanses of interstellar space. And finally, we have to ask ourselves, if there are rogue planets in our galaxy, could any of them ever drift close to Earth? Although the chances are slim, it is not impossible for a rogue planet to cross our solar system and temporarily become a new celestial neighbor. Should this happen, it would be a unique opportunity to examine one of these mysterious worlds at close quarters. In the darkness of interstellar space, rogue planets wander silently, waiting to be discovered. And while they may seem like lonely outsiders, these planets could hold some of the universe's greatest secrets, giving us a glimpse into worlds we've never before imagined. Exomoons, the hidden treasures of the cosmos. While planets are the main focus of our search for habitable worlds, there is another type of celestial body that could offer even more potential: exomoons. These are moons orbiting planets in other star systems, and although we have not yet definitively confirmed their existence, they are considered some of the most promising candidates in the search for life beyond Earth. When we think of moons, we often think of our own moon, a barren, rocky satellite with no atmosphere. But in our own solar system, moons like Europa and Enceladus have shown that moons can be much more than just inert chunks of rock. Liquid oceans could exist beneath the ice crusts of these moons, which are kept warm by the gravitational forces of their planets. If life is possible on these moons in our solar system, What could we find on exomoons orbiting planets around distant stars? Let's start with the basics. How do we find an exomoon? Discovering exoplanets is hard enough, and moons are even smaller and more difficult to detect. Most methods for discovering exoplanets are based on the transit method, in which a planet passes in front of its star and obscures the starlight for a brief moment. The same technique could be used for an exomoon, but the dimming effect would be even weaker, making it incredibly difficult to detect. Nevertheless, astronomers are still searching. In 2018, scientists using data from the Kepler Space Telescope announced the discovery of a possible exomoon orbiting the planet Kepler 1625b, about 8,000 light-years away. This potential exomoon, if confirmed, would be huge, about the size of Neptune, and could have a dense atmosphere, making it a mini-world in its own right. But why are exomoons so interesting for the search for habitable worlds? The answer lies in the fact that moons could offer conditions for life that differ from those on planets. On the one hand, moons could benefit from tidal forces. This is the process that keeps the oceans of Europa and Enceladus warm. When a moon orbits its planet, the gravitational forces of the planet stretch and compress the interior of the moon, generating heat. This heat can keep water in liquid form, even when the moon is far away from its star and should actually be frozen. Tidal heating could allow moons to maintain habitable environments in cold, distant orbits. Imagine a moon orbiting a gas giant in the outer reaches of a star system, where the sunlight is dim, but the interior of the moon is warm enough to sustain liquid water beneath the surface. This opens up the possibility of habitable moons in places where we would not expect to find life, at the edges of star systems, or even in binary systems where two stars orbit each other. Exomoons could also offer stable climates. Unlike planets, which can experience drastic temperature swings and weather extremes, moons may have more stable climates because the gravitational forces of their planets have a stabilizing influence. This could create environments in which life has more time to develop and adapt. And because moons orbit planets, they could receive light and heat from both their star and their planet, creating unique environmental conditions. Let's do a thought experiment. What if we were to find a large exomoon orbiting a gas giant in the habitable zone of a distant star? The gas giant itself could be uninhabitable, with a dense atmosphere of hydrogen and helium, but its moon could have a rocky surface and liquid water. The planet's gravity would protect the moon from some of the cosmic rays, and tidal forces could keep the moon warm while the planet orbits its star. This moon could have a dynamic atmosphere, perhaps even seasons, caused by its orbit around the gas giant, giving it varying amounts of sunlight. There could be vast oceans, forests, and perhaps even life forms that take advantage of both the moon's natural resources and the unique environment created by its giant neighboring planet. Of course, exomoons also pose challenges for life. A moon orbiting a giant planet would potentially be exposed to intense radiation emanating from the planet's magnetic field, similar to Jupiter's moon Io, which is bombarded by Jupiter's radiation. Possible life forms would have to find ways to protect themselves, for example by living deep below the surface or developing natural radiation shielding. In addition, moons could be exposed to extreme tidal forces, which could lead to geological instability and cause frequent earthquakes or volcanic activity. While tidal heating can keep a moon warm, too much of it could create an environment that is too unstable for life to form. Despite these challenges, exomoons remain one of the most promising frontiers in the search for life. The sheer variety of environments that moons could offer, from frozen oceans to volcanic landscapes, makes them exciting candidates for future exploration. And because moons are so common in our solar system, it is likely that they are just as common, if not more common, in other star systems. With advancing technology and our ability to detect smaller and weaker objects, we are likely to uncover more of these hidden treasures. The discovery of a single exomoon with an Earth-like atmosphere would revolutionize our understanding of where life could exist in the universe. And who knows, one day an exomoon could be the first place where we discover extraterrestrial life. In the vast depths of space, exomoons orbit their planets in silence, waiting for us to find them. And if we find them one day, they could offer us the key to the secrets of life beyond Earth. Hot Jupiters, unlikely worlds in extreme orbits. In our search for habitable worlds, there is one category of planets that stands out as a gigantic glowing exception: the hot Jupiters. These planets are gas giants like Jupiter, but orbit their stars extremely close, with temperatures so high that their atmospheres evaporate into space. Even though they are not candidates for life as we know it, hot Jupiters challenge our understanding of how planets form and evolve. They offer valuable insights into the diversity of planetary systems throughout the galaxy. Hot Jupiters were among the first exoplanets to be discovered, as their large size and proximity to their stars make them easier to recognize. The first confirmed hot Jupiter was 5.1 Pegasi b, which was discovered in 1995. This gas giant orbits its star in just 4 Earth days, at a distance much closer than Mercury's orbit around the Sun. On these planets, surface temperatures can reach thousands of degrees Celsius, with winds thousands of kilometers per hour strong, tearing apart the planet's upper atmospheric layers. What makes hot Jupiters so fascinating is the fact that they do not fit into our traditional model of planet formation. According to our understanding of the formation of solar systems, gas giants like Jupiter and Saturn should form in the colder outer regions of a system, far away from the intense heat of the star. But hot Jupiters break this rule and sit right next to their stars, where it is far too hot for gas giants to form. So how did they get there? Scientists believe that hot Jupiters migrated further out towards their stars after their formation. The most likely explanation is that gravitational interactions with other planets or the protoplanetary disk have caused these gas giants to move closer to their stars over time. This migration process may have been chaotic, with hot Jupiters pushing other planets out of the way or even throwing them out of the star system altogether. In some cases, this could explain the presence of rogue planets, planets that have been ejected into interstellar space by these massive wanderers. Hot Jupiters are fascinating not only because of their extreme environments, but also because of the dramatic effects they can have on their planetary systems. As these massive planets migrate inward, they can disrupt the orbits of smaller, potentially habitable planets, either throwing them out of the system or sending them into unstable orbits that lead to collision or destruction. In this sense, hot Jupiters are like cosmic wrecking balls, reshaping their star systems and possibly preventing the creation of habitable worlds. But hot Jupiters themselves offer a bizarre and extreme picture of planetary environments. The proximity to their stars leads to intense heating of their atmospheres, which can result in truly strange weather phenomena. For example, on the hot Jupiter HD 189733b, which is about 63 light-years away, temperatures can rise to up to 1,800 degrees Celsius. The winds on this planet blow at over 4,000 kilometers per hour, and scientists believe that glassy rain falls on it driven by these supersonic winds. Imagine standing on a planet where molten glass rains sideways in the glowing wind, an environment beyond anything we can imagine on Earth. One of the strangest things about hot Jupiters is their bound rotation. Just as the Moon always shows the same side to the Earth, hot Jupiters are also bound to their stars by tidal forces, which means that one side always faces the star while the other lies in eternal darkness. This leads to an extreme temperature difference between the day side and the night side of the planet. The day side is constantly bombarded by heat and radiation, while the night side remains cold and dark. The boundary between these two sides, the so-called terminator, could be characterized by extreme weather phenomena as winds transport heat from the burning day side to the frozen night side. Despite their hostile conditions, hot Jupiters teach us a lot about the diversity of planetary atmospheres. Many hot Jupiters have hazy, cloudy atmospheres that hide their surfaces from view, much like the gas giants in our own solar system. But under the intense heat of their stars, the chemicals in these atmospheres can behave in strange and unpredictable ways. For example, some hot Jupiters may have metal clouds or silicate particles in their atmospheres that reflect light and give the planet a strange, colorful appearance. In addition to their atmospheres, hot Jupiters give us clues about the magnetic fields of giant planets. The proximity to their stars exposes these planets to intense solar winds and magnetic interactions that could create auroras on them of a size beyond anything we have seen on Earth. These auroras could extend across the entire planet, lighting up the atmosphere in breathtaking bursts of color and energy. Hot Jupiters may not be ideal candidates for life, but they show us how wild and diverse planetary systems can be. Their discovery forced astronomers to rethink traditional models of planet formation, and they continue to provide valuable insights into the extreme environments that exist in the universe. As we search for habitable planets around other stars, the presence of a hot Jupiter in a system could tell us a lot about how that system formed and whether smaller rocky planets like Earth have survived the chaotic gravitational ballet that has shaped the orbits of these giant gas giants. Could there be moons around hot Jupiters? Perhaps some exomoons are hidden in stable orbits far enough away from the planet's hot heat to retain an atmosphere. Although it is unlikely that life could survive on the surface of a hot Jupiter, these moons could provide sheltered environments where the radiation and heat are less intense. Hot Jupiters remind us that the universe is full of surprises and that not every planet lives up to expectations. These massive glowing planets, orbiting far too close to their stars, are a testament to the chaotic and dynamic processes that govern the formation of planetary systems, and they challenge us to keep exploring the unknown. The future of exoplanet research. New eyes on the cosmos. Our journey through the multitude of planet types, from super-Earths to hot Jupiters, water worlds, and rogue planets, shows that the universe is far more diverse than we ever imagined. But we are only scratching the surface. The future of exoplanet research is incredibly promising, with new technologies and missions that will open up even more of the cosmos. In this chapter, we take a look at the exciting prospects that lie ahead when it comes to finding Earth-like planets and perhaps discovering life beyond our solar system. The James Webb Space Telescope, JWST, launched in December 2020, represents the next big step in space exploration. The JWST is equipped with instruments that are sensitive enough to detect chemical signatures in the atmospheres of exoplanets. This means that we can analyze the atmospheres of planets in unprecedented detail to look for signs of oxygen, methane, and other biosignatures that could indicate the existence of life. For example, if the JWST observes a planet with an atmosphere rich in oxygen and methane, this would be a strong indication of biological processes. On Earth, these gases are constantly being replenished by life. Plants produce oxygen through photosynthesis, and methane is released through both natural and biological processes. The detection of these gases on another planet would be a tantalizing hint that life might exist there. The JWST will also allow us to study planets in the habitable zone around nearby stars such as TRAPPIST-1, a star system that hosts 7 Earth-sized planets, 3 of which orbit the habitable zone. The ability to see these planets up close could bring us closer to discovering Earth-like worlds with the right conditions for life. What will we discover when we look into the atmospheres of these distant planets? In addition to the JWST, the European Space Agency's Plato mission is also due to be launched in the mid-20s and will focus on the search for rocky exoplanets in the habitable zones of sun-like stars. Plato will search for small rocky planets, those most likely to resemble Earth, and provide data on their sizes, masses, and orbits. In combination with the atmospheric analysis of the JWST, Plato could reveal the most promising targets for future exploration. At the same time, the LUVOIR telescope, Large Ultraviolet Optical Infrared Surveyor, which is currently under development, could revolutionize our understanding of exoplanets even further. LUVOIR is specifically designed to hunt exoplanets and is able to detect Earth-sized planets in the habitable zones of nearby stars. It will block the light from the parent stars so that we can see the faint glow of the exoplanets themselves, something that is almost impossible with current technology. Direct imaging is considered the holy grail of exoplanet research, as it would allow us to view these distant worlds at close range. Imagine a picture of an Earth-like planet orbiting a nearby star with visible continents, oceans, and clouds. With this kind of technology, we could finally answer the question, are we alone? As we prepare to send humans further into space, we will also look beyond the mere discovery of planets. There is growing interest in developing the ability to visit exoplanets or at least send probes to their star systems. The Breakthrough Starshot Initiative is one such project that aims to send tiny spacecraft, nanoprobes, to the Alpha Centauri system, the closest star system to Earth, which is about 4.2 light-years away. With the help of laser propulsion, these tiny probes could theoretically reach 20% of the speed of light, which would enable them to complete the journey in around 20 years. Once there, they could take pictures of the planets in the Alpha Centauri system and send the data back to Earth. Although this sounds like science fiction, the technology is making rapid progress. If Breakthrough Starshot is successful, it would be the first mission to leave our solar system with the specific aim of exploring an exoplanet system. What we might find in the Alpha Centauri system is unknown, but even a glimpse of the surface of a distant planet would revolutionize our understanding of the universe. There is also the exciting potential for habitable moons in systems like Alpha Centauri. If a planet is too close to its star, like a hot Jupiter, its moons could still be far enough away to support liquid water and life. These moons could be even more hospitable than the planets they orbit, making them fascinating targets for future missions. But the search for new worlds does not stop at Alpha Centauri. Ambitious plans to build massive interstellar spaceships capable of traveling to even more distant star systems are already being discussed. With a combination of advanced propulsion technologies and artificial intelligence, these ships could undertake long voyages, either with humans on board or unmanned, to explore planetary systems hundreds of light-years away. In the meantime, artificial intelligence and machine learning are already playing a major role in the search for exoplanets. With the vast amount of data collected by telescopes such as Kepler and TESS, scientists are using artificial intelligence to identify patterns and anomalies that could indicate the presence of a planet. These algorithms can process much more data than a human being, which speeds up the discovery process. Artificial intelligence could also help us to analyze the complex chemical compositions of exoplanet atmospheres. By simulating conditions on different types of planets, AI systems could predict which planets are most likely to support life. This would allow us to prioritize the planets that deserve the most attention in our search for habitable worlds. In the long term, terraforming distant planets could also be a new goal. While this idea is still largely speculative, some scientists believe that we may one day have the ability to alter the environments of other planets to make them more Earth-like. This could mean warming a cold planet by releasing greenhouse gases into the atmosphere, or creating artificial magnetic fields to protect the surface of a planet from solar radiation. Such projects would take centuries to complete, but the idea of transforming an alien world into a new home for humanity continues to capture our imagination. The future of exoplanet research is a combination of cutting-edge technology and human curiosity. With each new discovery, we expand the boundaries of what is possible and open up new dimensions of understanding about the universe and our place in it. As telescopes become more powerful and we continue to develop ways to explore distant star systems, the discovery of an Earth-like planet, perhaps even one teeming with life, seems less like a distant dream and more like an inevitable fact. In the great adventure of space exploration, the search for a new home is only just beginning. Terraforming, creating a new Earth. One of the most exciting and challenging ideas for making distant planets habitable is terraforming, the process of changing a planetary environment to make it suitable for human life. While it may sound like science fiction, terraforming is rooted in scientific principles, and researchers have already begun to investigate how we might one day alter the environments of planets like Mars to make them more Earth-like. What would it take to transform a hostile, harsh world into a thriving ecosystem that could serve as a home for people? First of all, we have to start with the most basic need: air. The Earth's atmosphere is a perfect balance of gases that support life, mainly nitrogen and oxygen. However, most other planets have atmospheres consisting of gases that would be toxic to humans, or they have no atmosphere at all. To terraform a planet, the first step would be to introduce gases such as oxygen and nitrogen to create a breathable atmosphere. Take Mars, for example. Its atmosphere consists mainly of carbon dioxide, with small amounts of nitrogen and argon, and it is extremely thin compared to the Earth's atmosphere. One possible method of terraforming Mars would be to release greenhouse gases such as carbon dioxide and methane into the atmosphere to create a greenhouse effect. This would trap heat, gradually warming the planet and densifying its atmosphere. Over time, this could raise temperatures enough to melt Mars's polar ice caps and release water vapor into the atmosphere, potentially creating conditions that allow liquid water on the surface. Scientists have proposed various ways to start this process, from using mirrors in space to direct sunlight onto the surface of Mars, to giant factories that release greenhouse gases into the atmosphere. The idea is that artificially increasing the amount of greenhouse gases in the Martian atmosphere would trigger a feedback effect that would lead to further warming, the melting of ice, and the formation of a denser atmosphere. However, even if we succeeded in warming Mars and densifying its atmosphere, we would still face the challenge of producing oxygen. One proposed solution is to use photosynthetic organisms such as algae and cyanobacteria to produce oxygen, similar to what plants do on Earth. These organisms could be introduced into the Martian environment, where they would gradually release oxygen into the atmosphere. However, this process could take centuries or even millennia before an oxygen-rich atmosphere like the one on Earth is created. In addition to air and heat, we need to ensure a stable water supply. Mars already has water ice in its polar ice caps and underground reservoirs, but it is unclear how much liquid water could exist on the surface. By melting the ice and collecting the water in reservoirs or channeling it through artificial rivers, we could create lakes, oceans, and rivers. However, it would be a challenge to keep this water from refreezing, and we would have to keep the planet's temperature stable in the long term. Another critical factor for terraforming is protection against radiation. Mars has no magnetic field, which means that its surface is constantly bombarded by harmful solar radiation. On Earth, our magnetic field protects us from this radiation, but on Mars, we would have to develop artificial methods to protect ourselves. One idea is to install magnetic fields in space that are placed between Mars and the Sun to deflect solar wind and cosmic radiation. Another possibility would be the construction of underground habitats where people could live protected while the surface is slowly terraformed. But terraforming is not just limited to Mars. Venus, our closest planetary neighbor, is another fascinating target for transformation, although the challenges there are even greater. Venus is similar to Earth in size and gravity, but its surface is an inhospitable hellscape with temperatures hot enough to melt lead and an atmosphere filled with thick clouds of sulfuric acid. If we could find a way to cool Venus and remove the excess carbon dioxide from its atmosphere, it could potentially become a habitable world. One radical idea is to build giant space mirrors that reflect sunlight away from Venus, which would cool the planet and collapse its atmosphere, similar to a freezer. Over time, the dense clouds would dissipate and we could begin to introduce water and oxygen. Another idea is to inoculate the atmosphere with microorganisms that could break down the carbon dioxide and sulfuric acid and convert them into less harmful compounds. In both cases, Mars and Venus, the process of terraforming would take centuries or even millennia. It is a long-term project that requires patience and constant effort over many generations. But the rewards would be enormous. A new Earth with blue skies, flowing water, and a breathable atmosphere where people could build cities, grow food, and thrive. Terraforming is not just about survival, it's about expanding the horizons of human civilization. By reshaping other planets, we could not only create a backstop for humanity should something happen to Earth, but we could also create entirely new ecosystems, with new life forms and new opportunities for exploration and discovery. However, ethical issues must also be considered. If we find life on Mars, even microscopic life, should we still terraform the planet? Some scientists argue that we should preserve Mars in its natural state and study its geology and any indigenous life without interference. Others believe that until we find life, Mars is a candidate for terraforming as long as we proceed responsibly. These questions need to be answered before we embark on such a monumental undertaking. But the potential of terraforming opens a new chapter in humanity's relationship with the cosmos. As our technology advances and our understanding of planetary environments grows, the dream of creating new Earths could one day become a reality. The planets of our solar system, and perhaps beyond, are waiting for us. Whether we reshape it, colonize it, or simply study it from afar, humanity's future in space is full of limitless possibilities. The Fermi paradox: where is the whole world? As we search for Earth-like planets and explore potentially habitable worlds in the universe, we inevitably come up against one of the most profound questions of all. If the universe is so vast, where is the rest of it? This question, often referred to as the Fermi paradox, was first posed by physicist Enrico Fermi in the 1950s. The paradox can be summarized as follows. Given the sheer number of stars in the Milky Way, estimated at around 100 billion, and the number of potentially habitable planets, it seems statistically inevitable that intelligent life exists somewhere out there. If this is true, why haven't we found any evidence of it yet? The paradox becomes all the more puzzling when you consider the age of the galaxy. The Milky Way is about 13 billion years old, which means that civilizations could have emerged billions of years before humanity. With so much time on our hands, it seems likely that an advanced civilization would have developed the technology to colonize the galaxy, or at least make contact with us. But so far we have heard nothing but silence. So where's the whole world now? There are a number of possible explanations for the Fermi paradox, and they range from the mundane to the extremely intriguing. Let's take a closer look at some of the most popular theories. One possibility is that intelligent life is extremely rare. While there may be millions of planets that could support life, the conditions for the emergence of intelligent civilizations may be far more stringent than we assume. Perhaps there is a critical hurdle that most life forms cannot overcome. For example, it took billions of years for complex life to evolve on Earth, and there were many times when it could have been wiped out by asteroid impacts, volcanic eruptions, or other catastrophic events. If even one of these extinction events had gone differently, the Earth might still be a planet of microbes. This leads us to the concept of the Great Filter, which states that there is an extremely difficult step in the evolution of life. The Great Filter could already be behind us. This would mean that the emergence of intelligent life is extremely rare, and that humanity has already overcome the biggest hurdle. Or the Great Filter still lies ahead, suggesting that most civilizations will eventually self-destruct before becoming spacefaring species. Nuclear wars, environmental disasters, or other self-inflicted catastrophes could be the fate of most advanced civilizations, which would prevent them from ever making contact with us. Another explanation is that intelligent civilizations exist, but are too far away for us to discover them. The universe is vast, and even if there are other civilizations, they could be thousands or millions of light years away from us. Given the limits of our current technology, we can only search for radio signals and other forms of communication in a relatively small area of the galaxy. It's possible that advanced civilizations are out there, but their signals haven't reached us yet, or we're just not listening in the right way. There is also the possibility that advanced civilizations are deliberately avoiding us. This is sometimes referred to as the zoo hypothesis, which states that the Earth is deliberately isolated from the rest of the galaxy. Just as we avoid interfering with a natural wildlife sanctuary, more advanced civilizations might observe us from afar and wait for us to reach a certain technological or social level before making contact with us. In this scenario, humanity is like an isolated tribe, unaware of the larger galactic civilization that is deliberately holding back. Another, somewhat darker possibility is the dark forest hypothesis, which describes the galaxy as a dangerous place where civilizations must remain hidden in order to survive. In this scenario, Intelligent species might actively avoid revealing their existence for fear that any message sent out might attract the attention of hostile forces. In a galaxy full of predators, the safest strategy might be to stay quiet. And perhaps that's exactly what other civilizations are doing. Could it be that we have not yet found an intelligent civilization because we are not looking in the right way? For most of the 20th and 21st centuries, the search for extraterrestrial intelligence, SETI, focused on finding radio signals, assuming that other civilizations would communicate in the same way that we do. However, it is quite possible that advanced civilizations use forms of communication that go beyond our current understanding. They could use quantum communication, neutrino radiation, or other exotic technologies that we have not yet developed. And then there is this more optimistic theory. We haven't found anyone yet because we are still at the beginning of our explorations. The Milky Way is a huge place, and we've only begun to scour a tiny fraction of the galaxy for signs of life. As our technology advances and more powerful telescopes and instruments are launched, we could soon begin to find the evidence we are looking for. It is quite possible that in the next century, we will discover radio signals, artifacts, or even extraterrestrial megastructures that indicate the existence of other civilizations. One of the most exciting projects in this field is the search for technosignatures, evidence of advanced technology on distant planets. While SETI has traditionally looked for radio signals, technosignatures could include anything from artificial light on the surface of a planet to massive structures like Dyson spheres built to power an entire star. If an advanced civilization existed long enough, it could have left behind such megastructures, and future telescopes could help us detect them. But what if we were looking for life that is completely different from us? The search for extraterrestrial intelligence was largely guided by the assumption that life elsewhere would be similar to life on Earth. We are looking for liquid water, Earth-like atmospheres, and carbon-based organisms because that is all we know. But life on other planets could take on completely different forms that we can't even imagine yet. Perhaps there is silicone-based life, organisms that thrive in liquid methane, or beings that exist in pure energy form. If we limit our search to Earth-like planets, we could miss the bigger picture. The Fermi paradox challenges us to think about our place in the universe and what the future of intelligent life might look like. Whether we are truly alone or part of a cosmic community, the search for extraterrestrial life forces us to ask profound questions about the nature of life, intelligence, and the future of humanity. With the progress of our technology and further exploration of the galaxy, we could finally solve the Fermi paradox. Whether the answer is that intelligent life is extremely rare, that civilizations are hiding, or that we have simply been looking in the wrong way, one thing is certain: the search for life beyond Earth remains one of the greatest mysteries of our time. Dyson spheres, harnessing the power of the stars. When we think about the potential of advanced civilizations in the cosmos, one of the most intriguing concepts is the Dyson sphere. This hypothetical structure, first proposed in the 1960s by physicist Freeman Dyson, represents the pinnacle of technological advancement, a civilization capable of harnessing the entire energy output of its home star. The idea of a Dyson sphere comes from the Kardashev scale, which measures the technological development level of a civilization based on its energy consumption. A Type 1 civilization is able to use all the energy available on its home planet, something humanity has not yet achieved. A Type 2 civilization can use the energy of its entire star, while a Type 3 civilization can control the energy of an entire galaxy. A Dyson sphere is associated with a Type 2 civilization that has developed the ability to capture and harness most, if not all, of its star's energy. So what exactly is a Dyson sphere? In its simplest form, it is a massive structure that completely encloses a star, captures its energy, and uses it to power an advanced civilization. The energy yield of a star like our Sun is around 384 septillion watts, an amount that far exceeds the energy requirements of any civilization on Earth. By building a Dyson sphere, a civilization could meet all its energy needs and potentially power technologies far beyond our imagination. There are several theoretical designs for Dyson spheres, and it is important to emphasize that Dyson never envisioned a solid shell around a star. Such a structure would be gravitationally unstable and also incredibly difficult to build. Instead, Dyson envisioned a swarm of individual satellites orbiting the star and capturing its energy. This type of structure is sometimes referred to as a Dyson swarm. A Dyson swarm would consist of millions or billions of solar collectors positioned at different distances around the star. These collectors could be giant solar panels or more advanced technologies that absorb the star's energy and transfer it to the civilization that built them. The swarm could be arranged in such a way that gaps are left between the satellites through which light can escape, making it visible from a distant point. This opens up an exciting possibility for astronomers. Could we discover a Dyson sphere or a Dyson swarm from Earth that an advanced civilization has built around its star? The answer could lie in the way the star's light is affected by the presence of such a structure. A Dyson swarm would block part of the starlight while the solar collectors orbit the star. From Earth, this could appear as an irregular dimming of the star, similar to exoplanets blocking the light of their star as they pass in front of it. However, unlike the regular dimming caused by planets, the dimming caused by a Dyson swarm would be more random and unpredictable, as the swarm does not move like a planet. A famous example of such irregular dimming is Tabby's star, also known as KIC 8462852, which lies about 1,500 light-years away in the constellation Swan. 2015, astronomers noticed that the star exhibited unusual fluctuations in brightness, leading some to speculate that this could be the result of a Dyson sphere or Dyson swarm. Although more natural explanations such as dust clouds are likely the cause, the case of Tabby's star shows that astronomers are actively searching for signs of advanced extraterrestrial technology. The possibility of discovering a Dyson sphere raises profound questions about the future of humanity and the existence of advanced civilizations. But how could a civilization build something as massive as a Dyson swarm? To construct a Dyson swarm, a civilization would need access to enormous quantities of raw material. One potential source could be the planets and moons of their star system. In the case of our solar system, for example, a Type 2 civilization could mine planets such as Mercury for their high metal content or dismantle smaller moons and asteroids to obtain the necessary resources. The swarm could be built up piece by piece over many millennia, with the first collectors gradually supplying the construction of further satellites with energy. A Dyson swarm would require an incredible level of technological sophistication. The satellites should be extremely efficient at capturing solar energy and transmitting it over long distances. They would also need to be able to self-repair and possibly even self-replicate, as the sheer number of satellites in the swarm would make manual maintenance impractical. But why should a civilization go to the trouble of building a Dyson swarm? The answer lies in the energy requirements of advanced technologies. As a civilization grows and develops advanced forms of artificial intelligence, interstellar travel, and planetary engineering, its energy requirements would increase exponentially. At some point, they would have to look for energy sources beyond their planet, and capturing the energy of their star would be the most efficient solution. A Dyson swarm could enable interstellar travel and allow civilization to explore and colonize other star systems. It could also support mega-engineering projects, such as the terraforming of planets or the construction of artificial habitats in space. With access to virtually unlimited energy, a Type 2 civilization could design its entire star system to suit its needs, possibly building huge space cities or even ring worlds, massive artificial structures orbiting a star and providing space for trillions of living beings. The idea of a Dyson sphere also raises philosophical questions about the future of humanity. Could we one day become a Type 2 civilization and build a Dyson swarm around our sun to harness its vast energy reserves? Some futurists believe this is possible, although it would require breakthroughs in materials science, energy storage, and automation. Even then, it could take thousands of years for humanity to develop the technology and resources to build such a structure. If we were to build a Dyson sphere, it would have a profound impact on life on Earth. With access to the sun's energy, we could power clean energy systems, eliminate resource scarcity, and develop advanced technologies such as quantum computing and interstellar communications. A Dyson swarm could also serve as a safety net for humanity by providing a source of energy, even if the Earth's resources were depleted or our climate became unstable. But what if we discovered that another civilization had already built a Dyson sphere? The discovery of such a structure would revolutionize our understanding of the universe and prove that intelligent life exists elsewhere. It would be a glimmer of hope, showing that civilizations can survive long enough to develop such advanced technologies. The search for technosignatures, signals from the stars. While Dyson spheres are one of the most ambitious technosignatures that could indicate the existence of an advanced civilization, the search for technosignatures is a vast and fascinating field of research. They are looking for signs of extraterrestrial technology beyond Earth. Unlike traditional biosignatures, which aim to detect biological life forms, technosignatures attempt to detect technological artifacts or byproducts of advanced civilizations, be it through radio waves, artificial light, or even evidence of large-scale cosmic engineering projects. For decades, the search for extraterrestrial intelligence, SETI, has mainly focused on detecting radio signals. This is because radio waves are an efficient way of transmitting information over long distances, and they can penetrate dust and gas in space with relatively little interference. In fact, the first potential evidence of an extraterrestrial signal comes from the famous WOW signal of 1977, which was received by a radio telescope in Ohio. The signal, which lasted 72 seconds, appeared to come from the direction of the constellation Sagittarius but was never detected again and remains a mystery to this day. Although the WOW signal has not been fully explained, it has inspired the modern search for extraterrestrial radio communications. Scientists at SETI and other research institutions continue to scan the skies and listen for unusual radio signals that could indicate the presence of an intelligent civilization. The challenge is that the universe is huge, and the chances of catching a signal in the right place at the right time are incredibly small. Nevertheless, the search continues, and new technologies are improving our ability to detect faint signals from the galaxy. In addition to traditional radio-based SETI research, researchers are now beginning to look for other types of technosignatures, such as optical signals. These could include laser pulses directed at Earth by an advanced civilization to communicate across interstellar distances. Lasers are highly focused beams of light that are ideal for transmitting messages through space, as they have less scattering than radio waves. An alien civilization could point powerful lasers at nearby star systems to send a light signal across the galaxy. Our search for optical technosignatures requires telescopes that are capable of capturing extremely short, bright flashes of light. These flashes could be only a few nanoseconds long, which is why the instruments that detect them have to be extremely sensitive. If we were to detect a laser pulse from another star system, this would be a strong indication that we are not alone. In addition to radio and laser signals, technosignatures could take many different forms, and as our technology advances, so does our ability to recognize them. One promising research approach is the search for megastructures such as Dyson spheres. As mentioned in the previous chapter, a Dyson swarm would block the light of its home star, causing an irregular dimming. By carefully observing the light curves of stars, astronomers may be able to detect the faint signs of these gigantic engineering projects. Interestingly, the Kepler Space Telescope, which was actually designed to search for exoplanets by detecting starlight attenuations, has provided a wealth of data that could be reanalyzed to search for technosignatures. Some scientists are currently scouring the Kepler data in search of stars that show strange, non-periodic dimming patterns that could possibly be caused by artificial structures. But what if extraterrestrial civilizations neither send out signals nor build massive structures? One intriguing possibility is that we could detect pollution from extraterrestrial technologies. Just as human activities on Earth generate industrial byproducts that pollute the atmosphere, advanced civilizations could generate technosignatures in the form of chemical pollutants or man-made gases that would hardly occur naturally. One example of this could be chlorofluorocarbons, CFCs, synthetic chemicals that are only produced on Earth through industrial processes. If we were to discover CFCs in the atmosphere of an exoplanet, this would be a strong indication of the existence of an advanced civilization. Large quantities of carbon dioxide or methane could also indicate industrial activities, even if these gases could also be produced by biological processes. By analyzing the spectra of exoplanet atmospheres with future telescopes, scientists could identify chemical fingerprints that point to extraterrestrial industry. Another potential technosignature could be artificial lighting. On Earth, our cities are illuminated at night by streetlights and other artificial light sources, which can be seen from space as the glow of the city. An advanced civilization on another planet could also use artificial light to illuminate its cities or even the entire planet. Astronomers could recognize this city light by searching for unusual light patterns on distant planets. The idea of looking for artificial nighttime lighting is particularly exciting because it allows a clear distinction to be made between natural light, such as the light from a star, and artificial light produced by intelligent beings. For example, the night side of an exoplanet, which is not directly illuminated by its star, should be dark. However, if we detect light on the night side of a planet, it could be an indication that an advanced civilization is using technology to illuminate their cities or the entire world. Yet another techno-signature could indicate large-scale stellar engineering projects. Imagine a civilization so advanced that it reshapes the stars themselves. This is the basis of the stellar lifting hypothesis, which proposes that a Type 2 or Type 3 civilization would be able to extract material from its star to use for construction projects or energy production. The process of star lifting would likely leave detectable changes in the spectrum or brightness of the star, which could allow us to recognize it from Earth. In addition to the search for technosignatures around distant stars, there is a growing interest in the search for evidence of extraterrestrial artifacts in our vicinity. One idea is that advanced civilizations may have sent probes or satellites into our solar system to monitor Earth or serve as way stations for interstellar exploration. These probes, also known as Bracewell probes, could be hidden in areas of space that we have not yet thoroughly investigated, such as the Kuiper Belt or the Oort cloud. If we were to find such a probe, it would be clear proof that we are not alone in the universe. Panspermia. Are we all aliens? As we continue to explore the possibility of life on other planets and moons, another intriguing theory emerges: panspermia. This concept proposes that life did not necessarily originate on Earth, but was instead brought here from elsewhere in the universe. According to the panspermia hypothesis, microbial life forms could travel across vast distances by hitching a ride on comets, asteroids, or even spacecraft, potentially spreading life throughout the universe. The idea of panspermia challenges the traditional notion that life originated in the Earth's primordial ocean. Instead, it suggests that life may be a cosmic phenomenon in which the seeds of life, simple, resilient organisms, are distributed throughout the universe and take root wherever they find suitable environments. So could it be that life on Earth actually originated from the stars? The theory of panspermia has a long history. The Greek philosopher Anaxagoras, who lived around 500 BC, the first to propose that life existed throughout the universe and was spread by seeds carried by celestial bodies. Although this idea was forgotten for centuries, it was revived in the 20th century. The first signs of new life appeared in the 19th century, when scientists began to consider the resilience of microbial life and the possibility that life might not be confined to Earth. There are different versions of panspermia, each proposing a slightly different mechanism for how life could spread through the universe. Lithopanspermia, for example, states that life could travel through space on rocks, especially on meteorites or asteroids. If a planet like Mars or Earth were to be hit by a giant object, debris containing microbial life could be hurled into space. Some of this material could land on other planets or moons and possibly carry life with it. Evidence of lithopanspermia comes from studies of meteorites found on Earth and originating from Mars. These Martian meteorites were hurled from the surface of Mars by asteroid impacts millions of years ago and finally reached Earth after a long journey through space. Surprisingly, some of these meteorites contain organic compounds, the building blocks of life. Although scientists have not yet found definitive proof of life in these meteorites, the discovery of organic materials suggests that the basic ingredients for life can survive a journey through space. Another form of panspermia, known as radiopanspermia, proposes that microbial life forms could be carried on tiny particles such as dust and accelerated across the universe by radiation pressure from stars. In this scenario, microscopic organisms could survive the harsh conditions of space, drift through the cosmos for millions or even billions of years, and eventually land on a suitable planet. While space is an extremely hostile environment with extreme temperatures, radiation, and a vacuum, some microbes on Earth have shown remarkable resilience, suggesting that life may be more robust than we think. Perhaps the most intriguing version of panspermia is directed panspermia, which proposes that life was intentionally spread by an advanced civilization. In this scenario, aliens would have deliberately inoculated planets like Earth with microbial life forms as part of a deliberate attempt to spread life throughout the universe. Although there is no evidence to support this theory, it raises profound questions about the origins of life and the possibility of intelligent design on a cosmic scale. An important argument in favor of panspermia is the resilience of extremophiles, microorganisms that survive under the most extreme conditions on Earth. Extremophiles have been found in environments that were once considered completely hostile to life, such as deep hydrothermal vents in the ocean, hot sulfur springs, and even the radioactive ruins of nuclear power plants. These organisms can withstand intense heat, pressure, radiation, and the vacuum of space, making them ideal candidates for interstellar travel. In fact, scientists have carried out experiments that show that certain microbes can survive in space for long periods of time. 2,000 years ago, researchers sent tiny aquatic animals known as tardigrades into space on a European space mission. The tardigrades were exposed to the vacuum of space, extreme cold and ultraviolet radiation, but survived for several days, and some of them even reproduced after returning to Earth. This experiment shows that life can survive in the harsh conditions of space, at least for a short time. But how likely is it that life was actually transferred from one planet to another? If we take a look at our solar system, we know that Mars, Earth, and Venus may have had similar environments in their early days, with liquid water and mild temperatures. It is conceivable that life originated on one of these planets and was then transferred to the others by asteroid impacts. For example, some scientists suspect that billions of years ago, Mars was a suitable place for microbial life forms when it had a more temperate climate. If there was life on Mars, a meteorite impact could have caused material containing Martian microbes to be hurled into space, some of which eventually landed on Earth. The question of whether life on Earth originated on Mars or vice versa has not yet been answered. But ongoing missions to Mars, including the Perseverance rover, are looking for evidence of past life that could help solve this mystery. If panspermia is correct, then life on Earth could not be unique. It could be part of a vast network of life that stretches across the universe, with planets infecting each other with life through cosmic collisions and interplanetary debris. This would mean that life is not an isolated phenomenon, but a fundamental component of the cosmos that arises wherever the right conditions are present. But how far could life travel through space? Even though we know that microbial life can survive for a short time in space, the distances between stars are enormous, and the journey would take millions or even billions of years. During this time, the organisms would be exposed to cosmic radiation that could damage their DNA. However, some microbes are able to fall into a dormant state in which they practically cease all biological functions. This allows them to survive extreme conditions over long periods of time. This ability could help them survive the long journey between the stars. Recent discoveries of organic molecules in interstellar space suggest that the building blocks of life are widespread in the universe. 2014 scientists discovered complex organic molecules in a disk of gas and dust around a young star using the ALMA telescope in Chile. These molecules are thought to be the precursors of life, and their presence in such a distant, early star system supports the idea that the ingredients for life are spread throughout the universe. So could it be that life is the rule and not the exception in the universe? If panspermia is a valid theory, it could mean that life is constantly transported from one place to another, taking root wherever it finds suitable environments. The panspermia hypothesis also has implications for our search for life on other planets. If life can spread through the universe, this suggests that life may be more common than we previously thought. Instead of looking for isolated cases of life on individual planets, we could look for a cosmic network of life connected by the vast expanses of space. The ultimate frontier, multiverse and parallel worlds. As we explore the mysteries of our universe, there is one theory that challenges our imagination more than any other: the concept of the multiverse. The idea that our universe could be just one of many, perhaps even an infinite number, challenges our understanding of reality itself. If the multiverse exists, then there could be other worlds, other Earths, and other versions of ourselves that exist in parallel but are completely out of our reach. The multiverse theory stems from several areas of physics and cosmology, all of which suggest that our universe may not be the only one. One of the best-known versions is the many worlds interpretation of quantum mechanics, which was proposed in 1957 by the physicist Hugh Everett. This interpretation states that every time a quantum mechanical event occurs, such as a particle being in one of two possible states, the universe splits into multiple versions, one for each possible outcome. This leads to an infinite branching of realities in which every possible version of events is lived out in a parallel universe. Imagine that every decision you have ever made, every yes or no, every choice to turn left instead of right, has created a new universe. In one universe, you might have taken a different path in life, while in another, you would have made the same choices as in this one. If you multiply this by the countless quantum events that happen every moment, you get an idea of the enormous size of the multiverse. But the many worlds interpretation is only one version of the multiverse theory. Another idea comes from cosmic inflation, the process that scientists believe caused the universe to expand rapidly in the first moments after the Big Bang. This theory suggests that the rapid expansion of space may have created bubbles of space-time, each forming its own unique universe. In this scenario, our universe would be just one of many bubbles, each with its own physical laws, constants, and conditions. This version of the multiverse is often referred to as the bubble universe or eternal inflation. In this model, the Big Bang that created our universe was not a unique event, but just one of countless Big Bangs that took place in different regions of space-time. Each new bubble that is created could become its own universe, with some bubbles being hospitable to life and others not. The vast majority of these universes could have physical laws that are completely different from ours. Perhaps stars don't form there, or gravity is so weak that matter never comes together. However, in some rare cases, the conditions could be just right for stars, planets, and life to form, just like in our universe. One of the most fascinating implications of the multiverse is the idea that there could be parallel versions of Earth. If the laws of physics are similar in different universes, it is possible that Earth-like planets also exist in other realities. These parallel Earths could be very similar to ours, but with subtle or less subtle differences. Perhaps in one universe, the dinosaurs never died out, and intelligent life evolved from reptilian ancestors. In another universe, human history might have been completely different, with different civilizations rising or technological advances made at different times. In some parallel universes, everything could be almost identical to our own, except for one small detail. Maybe you have a different profession, or humanity has already colonized Mars. The possibilities are literally infinite and are only limited by the laws of physics and the initial conditions of each universe. But can we ever discover these other universes or interact with them? At present, the multiverse theory remains highly speculative, and we have no direct evidence that other universes exist. However, some scientists believe that clues could be hidden in the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates our universe. Small variations in the temperature of the CMB could theoretically indicate interactions between our universe and neighboring universes, like the faint imprint of a cosmic collision between two space-time bubbles. Further potential evidence for the multiverse could come from the behavior of black holes. Some physicists have suggested that black holes could serve as gateways to other universes. When matter falls into a black hole, it is compressed to an incredibly dense form and disappears from our universe. But what if this matter is ejected into another universe and forms the seed for a new Big Bang? This idea, known as black hole cosmology, suggests that each black hole could be the beginning of a completely new universe that exists separately from our own. The multiverse also raises profound philosophical and existential questions. If there are infinite versions of reality, each with a different version of you, what does that say about your identity? Are you just one of many versions of yourself, or is this particular version of you unique in some way? And what about free will? If every possible decision leads to a bifurcation of universes, do you really have control over your decisions, or are all possible outcomes in a universe inevitable? These are questions that both philosophers and scientists are grappling with as they ponder the implications of the multiverse. From a scientific point of view, the challenge is to find ways to test this theory. At the moment, the multiverse is more of a mathematical concept than a proven reality, but advances in quantum mechanics, cosmology, and string theory may one day provide us with the tools to explore these alternative realities. In particular, string theory offers another possible explanation for understanding the multiverse. According to string theory, the basic building blocks of the universe do not consist of particles, but of tiny, vibrating strings of energy. These strings can vibrate in different ways, and thus generate the various particles and forces that we observe. String theory also predicts the existence of additional dimensions that go beyond the known 3 dimensions of space and 1 of time. Some versions of string theory propose that our universe is just a brane, a multidimensional object, floating in a higher dimensional space, and that other branes or universes could exist alongside ours. In this model, universes could exist parallel to ours in a higher dimensional space, separated only by a small distance that we cannot perceive. These universes would be invisible to us, but could occasionally interact with each other, causing strange phenomena that we can observe in our own universe. For example, some scientists speculate that gravity, which is much weaker than the other fundamental forces, may be leaking into neighboring universes, which explains why it appears so weak in our universe. Whether through quantum mechanics, black holes, cosmic inflation, or string theory, the idea of the multiverse expands the boundaries of our understanding of reality. If it turns out to be true, it would mean that the universe we see and experience is just a tiny slice of a much larger, more complex, and infinitely diverse cosmic landscape. In a way, the multiverse theory is reminiscent of old philosophical ideas about the nature of existence. Many cultures and belief systems have postulated the existence of alternative worlds or realms beyond our own. Whether in mythology, religion, or science fiction, the idea of parallel worlds has fascinated mankind for thousands of years. The multiverse theory brings this concept into the realm of modern science and offers a tantalizing glimpse into what might lie beyond the boundaries of our universe. But what would this mean for our search for a new home? If the multiverse exists, it is possible that there are not just a few Earth-like planets in the cosmos, but an infinite number of Earths that are all only slightly different from each other. In one universe, we could already be exploring the stars with advanced spaceships, while in another, we are still struggling with the basics of interstellar travel. The multiverse opens up an overwhelming variety of possibilities, each more fascinating than the last. As we continue to explore the universe and search for new Earth-like planets, we should also be aware that the ultimate frontier may not be out there in the stars, but in the vast network of realities that could exist beyond our own universe. Whether we will one day find a way to interact with these parallel worlds remains to be seen, but the very idea of it broadens our view of what the universe or the multiverse might hold. Exotic life forms. Imagining life beyond Earth. On our journey through the universe, we ask ourselves one of the most fascinating questions. What could life on other planets look like? While we have spent most of our time searching for Earth-like worlds, the universe could harbor life forms completely unlike anything we can imagine. Exotic life forms, organisms that exist in environments radically different from those on Earth, challenge us to think beyond the familiar and explore possibilities for life in conditions we once considered uninhabitable. On Earth, life is based on carbon and depends on water. This has shaped our search for extraterrestrial life and has led scientists to focus on planets with liquid water and temperatures similar to those on Earth. But as we've explored extreme environments on our own planet, we've discovered organisms, called extremophiles, that thrive in conditions far removed from what we consider normal for life. These extremophiles have shown us that life is incredibly adaptable and could possibly exist in forms that we do not yet know. One of the most exciting places to search for exotic life is Saturn's moon Titan. Titan is unlike any other place in our solar system. It is the only moon with a dense atmosphere, and its surface is crisscrossed by lakes and rivers. But there is a catch. These lakes and rivers are not filled with water. Instead, they consist of liquid methane and ethane flowing at temperatures much colder than anything we experience on Earth. While the temperatures on Titan are too low for liquid water to exist, some scientists believe that life could still exist there using liquid methane as a solvent instead of water. This would require a completely different type of biology, one that is adapted to the extreme cold and uses methane in its metabolic processes. If such life exists, it would be completely different from anything we know on Earth, possibly consisting of cells based on hydrocarbons rather than carbon and water. Another fascinating candidate for exotic life is Venus, a planet that we have long considered inhospitable. The surface of Venus is an inferno with temperatures hot enough to melt lead and clouds permeated with sulfuric acid. But recent discoveries have raised the possibility that life could exist high in the atmosphere of Venus, where conditions are much cooler and more stable. In the year 2020, scientists discovered phosphine, a gas associated with biological processes on Earth, in the atmosphere of Venus. While the presence of phosphine is not definitive proof of life, it has sparked interest in the idea that there could be microbial life in the clouds of Venus, suspended in droplets of sulfuric acid. If life could survive in the harsh conditions of Venus's atmosphere, or Titan's methane lakes, it would force us to rethink our assumptions about what makes a planet habitable. Life might not even need water or even carbon. Some scientists have speculated about the possibility of silicon-based life, an idea that has become popular in science fiction. Silicon, like carbon, can form complex molecules and is abundant in the universe. But silicon chemistry is less versatile than carbon chemistry at Earth-like temperatures, making it less likely to support life as we know it. But under the extreme conditions of another planet, perhaps at high temperatures and pressures, silicon-based life could thrive. Another possibility is ammonia-based life. Ammonia can act as a solvent in a similar way to water and remains liquid at much lower temperatures. On a cold planet or moon, ammonia-based organisms could use ammonia instead of water, and thus survive in environments that would be too cold for most life forms on Earth. This opens up the possibility of finding life on icy moons such as Europa or Enceladus, where there could be underground oceans of water mixed with ammonia and harboring microbial life. Not forgetting the potential for life in even more extreme environments, places like gas giants or rogue planets drifting through space. On gas giants such as Jupiter or Saturn, life could not exist on the surface, but deep in the dense atmosphere. These organisms could live in the upper layers of the atmosphere like floating plankton and feed on chemical compounds transported by the planet's winds. The extreme pressure and storms of a gas giant would pose challenges for life, but it's possible that organisms could evolve to take advantage of these conditions, much like the deep-sea creatures on Earth that thrive around hydrothermal vents. In the case of rogue planets, planets drifting through space without a star to warm them, life would have to rely on internal heat sources, such as geothermal energy or the decay of radioactive elements. While the surface of a rogue planet would be frozen and inhospitable, there could be subsurface oceans warmed by the planet's core, similar to Europa's ocean beneath its ice crust. Life on a rogue planet could resemble the extremophiles on Earth, who live in complete darkness and feed on chemical energy rather than sunlight. And what about life forms that are completely beyond our imagination? Organisms that do not follow any of the biological rules we know. One possibility is that advanced extraterrestrial life has evolved beyond biological bodies and moved on to artificial intelligence or some other form of post-biological existence. These beings could exist as self-replicating machines that travel through the galaxy in search of resources or knowledge. They may have developed technologies that allow them to thrive in environments that would be lethal to organic life, such as the vacuum of space or the surface of a neutron star. If such life forms exist, they could leave us not biological but technological signatures. These could be radio signals, megastructures, or even artifacts left behind on other planets or moons. The discovery of such techno-signatures would definitively prove that life goes far beyond the organic creatures we know on Earth. The search for exotic life also forces us to question the limits of human understanding. As we explore the universe, we are limited by our own biology and the conditions we need to survive. But what if there are life forms that experience the universe in a completely different way? A being made of plasma or living in the atmosphere of a gas giant could perceive the world through senses that we do not even understand. It could communicate through electromagnetic fields, or its consciousness could be spread across wide areas of space instead of being confined to a single body. Understanding such life forms would require a complete change in the way we think about biology, intelligence, and even consciousness. But the possibility that life could exist in such diverse and unimaginable forms is one of the most exciting aspects of space exploration. It reminds us that the universe is full of unknowns, and we are only scratching the surface of what is possible. As we continue to search for new home worlds in the cosmos, we must remain open to the idea that life is much more adaptable than we once thought. Planets and moons that we once thought were barren could harbor thriving ecosystems hidden under ice, in the clouds of distant worlds, or deep in alien oceans. Some life forms might not even need planets. They could be drifting through the vastness of space, waiting to be discovered by us. The universe is full of possibilities, and the discovery of exotic life would change our understanding of biology, evolution, and the nature of life itself forever. In the end, the search for exotic life isn't just about finding other organisms. It's about expanding our understanding of what life can be and realizing that we may not be the only strange creatures in the cosmos.